Greetings, Calculus 2 students, and welcome to this extra example video. At the time of this video, we're on the cusp of entering our major unit of the course on series. Now, it's probably going to be surprising then that you're going to feel like you're back in Calculus 1 because in Calculus 1, you approximated functions using linear approximation with their tangent lines, and that's what we're going to be doing in this video. But of course, this is opening a can of worms that we are going to take that idea and run with it and go way, way beyond what you did with it in Calculus 1. Still, it's good to start with something familiar. So let's see where our journey begins in series. Really, the whole enterprise of series, as they're considered in calculus, starts with the following question. Wouldn't it be nice if all functions were polynomials? And I think that's kind of a no-brainer. The answer is, well, yeah, because of all the functions that you deal with, and you've dealt with some pretty complicated ones, polynomials tend to be the easiest general class of functions, right? They're very easy to differentiate. They're very easy to integrate. They're relatively easy to, do things like graph and compute limits of them and so on. So they're pretty nice functions all in all. Especially for calculus purposes. And you'd say, yeah, but that's just not reality, right? We've got transcendental functions, trig functions, exponentials, logarithms, all that kind of stuff. None of those functions are polynomials. But here's where the first twist comes in, because it does turn out, amazingly enough, that just about all the functions that you're interested in studying in calculus can be thought of as polynomials. Now you're wondering, what's the catch? Because we know they're not polynomials. Okay, yeah, there's a couple catches, but they're not bad. Okay, main one is we've got to expand our notion of polynomials a little bit to allowing polynomials with infinitely many terms. That's going to seem a little weird, take a little getting used to. But hey, if you have polynomials kind of getting more and more terms, why not let them have infinitely many? That's kind of the whole concept behind series as we're going to look at them. The other thing we have to do is limit ourselves to an appropriate interval. A polynomial has domain equal to the set of all real numbers. We're not going to be able to get all of our functions to be approximated nicely by a polynomial or equal to a polynomial on that entire real line. So we got to temper our expectations with a little bit of reality, but this is still kind of an intriguing prospect. Okay, but instead of launching right into getting polynomials that are equal to all of our favorite functions, we're going to take things one step at a time and do something a little simpler and just look at approximating functions using polynomials. This is still an interesting concept because, again, we're not approximating values here. We're approximating functions at large. Okay, so here's where the Calculus 1 idea comes into play. Remember in Calculus 1 doing linear approximation? This is a way of approximating any differentiable function using a linear polynomial, hence the name. And the linear polynomial that you want to use is the one that corresponds to the equation of the tangent line to the graph of that curve at a given point. So you want to focus on a given point here. Let's say a, f of a. F is differentiable at a. And then if you think of your equation for a tangent line, its right-hand side is going to be f of a plus f prime of a times x minus a. Hopefully that looks familiar. But on the left side, instead of just putting y, we're going to put L of x. We're defining a function L here. And L is called the linearization of f at a. In some sense, you're turning f into a linear function or replacing it with a linear function, which is its linearization. It seems like maybe it's kind of not fair, it's whatever function it is, we're turning it into a linear function. But at the end of the day, we're approximating the function with that linear function. Okay, now we're going to do the same thing, but we're going to have a different name for it. The linearization is also called the degree 1 Taylor polynomial for f centered at a, and we will denote it by t sub 1 as well as by L. Okay, so not surprisingly, the formula here is the same. And you probably realize that, introducing this new terminology, this new notation, this is something that we're going to work to generalize, okay, beyond degree 1. But for now, we'll focus on that degree 1 situation. Okay, so that's why the alternate notation. We also have A here. A, of course, is that point of tangency that we're using. We're finding the tangent line at. We will call that the center of this Taylor polynomial. And I hope it'll become really clear as we go on why center is just the right name for this A value. Okay. Now, with that idea in mind, let's look at a classic example. And for that, we are going to look at the exponential function base e. Okay, and we're going to center at a equals 0, kind of keeping things as simple as we can here for our first example. All right, so let's compute the degree 1 polynomial, Taylor polynomial for f, centered at a. So we know that the equation for that, the general form of it, is going to be that t1 of x is going to equal f of 0. So our a here is 0. So we'll put that in right away. Plus f prime of 0 times x minus 0. Again, because our center is at 0. So it keeps things nice and simple. And as far as our derivative and our values, well, we know that the derivative of e to the x is just e to the x. And so f prime of 0, that's e to the 0, which is 1. And for that matter, that's giving us our f of 0 right away. That's also going to be 1. And so we can put everything in there and get that t1 of x is 1 plus x. Maybe one more step here to get to that. F of 0 is 1. F prime of 0 is 1. And then we've got times x minus 0, it's going to be x. So yeah, it really quickly boils down to t sub 1 of x equals 1 plus x. Okay, we do a graph of this. Let's see. So things are mostly going to be above the x-axis here. Kind of focusing in on 0, x equals 0. Okay, so if 1 is, let's put 1 there. And so that means probably negative 1's about over there. Our exponential function, as you know, that's, if possible here, going to exhibit some exponential growth. Like so. There's y equals e to the x. Rough sketch of it. And then our linear approximation, or our degree 1 polynomial here. Let's see, let's use purple for that. That's going to be right here. Pretty hard to draw a straight line on this screen. But there is y equals t1 of x, which is the line with slope 1 and y-intercept 1. Okay, so there we go. Now, again, inaccuracies of my diagram aside there, I'm going to claim that of all lines that go through the point 0, 1, which our exponential function does as well, so we're tangent at the point of tangency here, y equals t1 of x is the one that best approximates e to the x. Now, how can I say that? It's the one that best approximates it. Well, one key piece of evidence. Okay, so first of all, it has the same value as e to the x does at our center, which is 0. So e to the 0 is 1. T sub 1 of 0 is also equal to 1. So that's good. But it also has the same slope. We know that the slope of our tangent line is 1. And we know then, by definition, the slope of the exponential function base e is also 1. So not only has the same value, it has the same sloping behavior. Okay, and it is the only line through 0, 1 that has the same slope as e to the x there. So that's already pretty convincing. Another thing you could do, and I encourage you to try this on your own, is to plot these two graphs on a calculator, on Desmo, something like that, and then zoom in towards that point of tangency 0, 1. And I claim that as you do that, as you zoom in further and further, eventually you will not be able to tell the difference between the graph of the exponential function and the graph of the degree 1 Taylor polynomial. But again, that's on a very small scale. Okay, hopefully it's convincing that this is a good approximation, but at the same time, if we do the opposite and we zoom out, you get a really different story there. As you zoom out, you find that, yeah, on the broad scale, this line is really behaving very differently from the exponential function that's got exponential growth out in one direction, exponential decay out in the other direction. The line doesn't do any of that stuff. So broadly speaking, it's not that great of an approximation. But right near that point of tangency, it is a very good approximation, such that you can hardly even tell the difference. Another way, besides a graph, to take a look at that comparison is to just look at some values. Compare values of e to the x and t sub 1 of x for some different x values. And what you can see on the table here, where, by the way, all the numbers where needed are rounded to 6 decimal places. What you can see is that if we look at x values which are very near that center, near that point of tangency, the values are very close together. So our Taylor polynomial gives a great approximation. And the way that we can really see and measure how good of an approximation it is by looking at the error. You see that in the right-hand column over here. That's our key thing to look at. Recall that the error of an approximation, we've seen these before in other contexts. It indicates how accurate an approximation is. And what the error is, it's what you'd have to add to the approximation to get the actual value. So the error is computed by subtracting the approximation from the actual value. So here we can see that all of our approximations are underestimates, which makes sense, again, looking at that graph. And they're pretty good. You know, errors of 0.001 or so and less than 0.005 when we're near our center. Those are very good, very close approximations. As you move further over, like to x equals 0.4, now you're 0.4 away from your center, the approximation is still pretty good, not as good for sure. Now it's off by almost a tenth, about 0.09. And if you go really far, go rogue here, get far away from the center, go over to like x equals 3, here you can see that, yeah, this approximation is basically worthless on that kind of a scale. The error is over 16. It's way bigger than the approximation itself. So again, it just goes to show you get good approximation here if you stick near that center. You wonder, though, could we do better here? Could we do an approximation that is even more accurate and stays better, further away from that center? The answer is yes, and we'll see how to do that. It's to be continued until our next video, where we approximate using a quadratic polynomial instead of a linear one. See you then.